Hello everyone. In this short video we're going to look at how we can calculate our neutral axis depth from S concrete. In this case here we're going to be using a square 700 by 700 millimeter reinforced concrete section. As you can see, it's a beam cross section where I have top and bottom rebar, and in this scenario the rebar layout is not identical on the top and bottom, so I have 4 25M bars on the top and 8 30M bars on the bottom. And the scenario that I'm describing here, we're going to be looking at a single load. So if I go to the Edit Loads dialog, we're going to be looking at the scenario where we have a single moment in this scenario in the MZ direction. And as you can see from the MZ direction, we're basically bending about the weak axis of this beam. And so we want to determine not only the neutral axis depth, but which bars are going to be in tension versus compression when resisting this type of load. And this is done using S Concrete's N versus M diagram. So if we go to the results menu and we go to the N versus M diagram, we can see here the interaction diagram that's come up. It's looking at our applied loads and looking at the correct theta angle for this applied load, where we have, again, just a single MZ value of 330 kilonewton meters. And I can see my interaction failure envelope. And S Concrete will actually use a strain compatibility approach to determine the axial load and moment capacity of a given section, where it's assuming here that the planes are going to remain plane before and after bending. Now in this scenario, I might be interested in understanding which beams, or which bars rather, are going into tension or compression, as it may not necessarily be as cut and dry as if I had bending about the z-axis here, as you can see. So you can imagine if I had bending about the other axis, it would be pretty clear that either the top or bottom bars are all in compression or tension. However, it's not so cut and dry in this scenario. But what I can do is I can use this interaction diagram, which is interactive, and I can right click on the location of my applied load case here. So I'll just right click and I'm going to say I want to view the normal envelope. And when we do that, you'll notice here that it's come up with some data points revolving around that normal envelope. So here I can see, first of all, the top bars that I have, the bottom bars, the stirrups that I have as well. And then I can see the point that I clicked on, as well as different data related to that point in the interaction curve. So I can see here the C value, which is my neutral axis depth of 201 millimeters. I also have my effective depth, 493 millimeters, and the area of steel in tension, as well as the strain. So with this information in mind, we have a knowledge of the relationship between the neutral axis depth and the compressive block depth, where we can calculate the compressive block depth by the product of the beta 1 value multiplied by my neutral axis depth of 201 millimeters. Now in this scenario, I'm using a 40 MPa concrete, so my beta 1 value is 0.87. And this will lead me to a neutral axis depth of 174.9 millimeters. Now I'm just going to flash on screen here a bit of a description of the different spacings of all the bars, and we can help use that to determine where our compressive block would fit into this. So we have a 40 millimeter cover. We have a diameter of our ties at 11.3 millimeters. And on the bottom we have 8 30M bars, so each one is 29.9 millimeters in diameter, and they're spaced 51.2 millimeters apart. On the top we have a 40 millimeter cover as well, like we saw, it's same 11.3 millimeter ties diameter, and then we have 25.2 millimeter bars, but they're further spaced apart at 165.5 millimeters. So I'm going to switch to a different view here, and if we switch at the out the view here and we look at basically drawing our compression block onto this with the understanding of our bar spacing and so on, and the knowledge that our compression block depth is 174.9 millimeters, it's going to encapsulate just past the second bar from the far left side of my beam. And on the top, it's going to encapsulate just a single bar on the top left side of my beam. So with this knowledge here, we can say that 3 total bars are in the compression zone. So that's two 30M bars and one 25M bar. And that leaves three 25M bars and six 30M bars in the tension zone. And we can then determine the amount of steel that's in tension that we can use for things like longitudinal steel requirement checks and more. So that might be a handy little way to validate this information for yourself. And again, this is all available through the interaction diagrams within S Concrete. If you'd like more information, again, please feel free to check out the other videos on this channel or our website, and we'd be happy to help answer any questions you might have via technical support.